functions and polynomial functions. We're going to start with power functions, which are monomial functions, which means they just have one term. So, for instance, we have x to the n, where n is your exponent, can be any power, and there's no other terms with it. This is basically like your polynomial parent function. And then when you build from that, you get different types of graphs. But we're going to start with the power functions that have an even power. So if my n is an even number, I'm going to have a graph that's similar to a quadratic. So if you look here, the y equals x squared is the red graph. If I change the power to the fourth, so I'm increasing the power, that is your blue graph right here. The green one is the x to the sixth, and the purple one is x to the eighth. So what's happening as your power increases is notice that it gets flatter around the origin. But it's also because the power is increasing and it exponentially, it's getting thinner because the y value, or the f of x value, is increasing at a faster rate. So out to the side, if you want to write as the power increases or exponent increases, it gets flatter around the origin. And it gets thinner because it's increasing faster. Also, depending on whether your term is positive or negative, so if I have a positive x squared, or actually x to the n, so it can be any power, my graph is going to look like a quadratic where both ends are going to be going to infinity. So notation wise, I say as x approaches infinity, so as x goes to infinity, my f of x approaches infinity. And then the same thing for the other way, as x goes to negative infinity, f of x approaches infinity because it's going up. Now, if I change that to a negative x to the n, it's going to flip it over just like if you had a negative x squared. So as x approaches infinity, it's going to flip that graph down so that f of x approaches negative infinity. And also as x approaches negative infinity, f of x approaches negative infinity. So that's as long as n is even, and depending on whether it's positive or negative, it tells you what the ends are doing. Now when we look at a power function where n is odd, so 3, 5, 7, or 9, it does basically the same thing. It flattens around the origin, but increases at a faster rate. So my black function is my x cubed. The red would be the x to the fifth. I think the blue is right on the inside of that, is the x to the seventh. And the green's the very thinnest one, is the x to the ninth. Now, depending on what the sign of our x to the n here, again, and this time we're dealing with an odd, they're going opposite directions. So as x is approaching positive infinity, f of x is approaching infinity. But if you're going to negative infinity, your f of x is going to negative infinity also. So as x approaches infinity, f of x approaches infinity. But as x goes to negative infinity, f of x goes to negative infinity. So they're going opposite directions. Now, if you had a negative x to the n, where n is odd, it's going to flip that around so that if x approaches infinity, your f of x will be going to negative infinity. And as x approaches negative infinity, f of x goes to infinity. So it would just be flipped the opposite direction. This side would go down, and this side would go up. So that's when you're talking about the end behavior of a power function. Now let's talk about polynomials now. I know this notation looks scary, but it's not any different from the quadratic notation where you use f of x equals ax squared plus bx plus c. A, b, and c are your coefficients. Well, for a polynomial function, it could have many, many terms. So here I've got 1, 2, blah, 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 on and on, however many terms it has. I could have more terms than I have letters in the alphabet. So what we've done is we've named those coefficients with a subscript of whatever matches our degree. So a sub n is just some number that goes with x sub n. And then you're going to count down in descending order, and I've got a sub n minus 1 goes with the n minus 1 power. And then you continue down until you're got x squared, x, and then just x to the 0 power is 1. So that would just be our constant, like your c is. So it's a little scary notation, but it's just a way to write a generic polynomial function. What I want you to get from this is know that the biggest degree is attached to your leading term. That's what makes it the leading term, and your leading coefficient is the number in front of it. That right there is going to tell you a lot of what the graph of the function is going to look like. So when we look down here at these examples, I want you to pick out the leading coefficient, the degree, and the leading term. So if we look at this one, it's in descending order. So 5x to the 6th is going to be our leading term. Our degree, which is n, we'll call our degree n, is 6. And our leading coefficient, I'm just going to put LC, is going to be 5. So that's all that I want for these next couple examples. Just be careful, they're not always in order. So make sure you find the biggest degree. That's your leading term. So our n here is 3, and our leading coefficient is -4. Here we've got n equals 5 and a leading coefficient of 5. And then the last one here, the p to the 3rd power is our highest power. So our n is going to be 3. Our leading coefficient is going to be -1. So you'll have a couple homework problems that just ask you to break down and define the leading term, the leading coefficient, and the degree of the polynomial. So when you look at like this first one, that would be a 6th degree polynomial. The second one would be a 3rd degree. third would be a fifth degree, and the last one would be a third degree. So it goes by what your largest power is. Now, when you look at a polynomial, there's no breaks, holes, or gaps. So if you're looking at these graphs, this first one would be a polynomial, but the second one would not because it's got a break where it jumps from one graph to another, which is nice because if a polynomial has no breaks or holes or gaps, then there are no problem spots. So on a polynomial, your domain is always going to be all real numbers or from negative infinity to infinity. Also, all polynomials have round, smooth turns. There's no sharp turns like you have on an absolute value. That would not be a polynomial. But this second one would be a polynomial because all of the turns, they can be sharper turns or quick turns, but they have to be rounded. It can't come to a V like that. That's what makes it not a polynomial. So an absolute value would not be a polynomial function. Moving on, concerning turning points and x-intercepts, a polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. So at most means that that is the most. It can have less, but it can't have more than n intercepts or n minus 1 turning points. So if I just look at this polynomial function, my leading term is x to the fourth. So my n is 4, which means I have at most 4 x-intercepts. And then n minus 1 is going to be 4 minus 1, which equals 3. I'm going to have at most 3 turning points. So if you look at the graph of this, I do have 1, 2, 3, 4 x-intercepts, and then I've got 1, 2, 3 turning points. So that's the most it can have. Now it doesn't have to have 4 and 3. It could have less, but this polynomial does have 4 x-intercepts and 3 turning points. So for example here, if I've got f of x equals negative 3x to the ninth, that's my highest degree. What that tells me is, when I'm talking about x-intercepts and turning points, that's going to have at most 9 x-intercepts and n minus 1. So 9 minus 1 is 8 turning points. So at most x-intercepts, 9 x-intercepts, and at most 8 turning points. And like I said, it doesn't have to have 9 and 8, but it can't have more. It could be less, but not more. On the next example, find your highest power, which is your 14x to the 12th power. So this one will have at most 12 x-intercepts and 11 turning points. Now, the next thing we're going to look at is the leading coefficient test, which tells us about the long run behavior of a polynomial. And we talked about this earlier when we were talking about our power functions, what's happening on the ends as x approaches infinity or negative infinity. So you've got a couple situations here. If n is odd, you're similar to the x cubed. So if n is odd and you have a positive coefficient, it's going to be similar to x cubed. So that would mean as x approaches infinity, the f of x approaches infinity. As x approaches negative infinity, f of x goes to negative infinity. Now that polynomial function could be doing all kinds of twists and turns in between the ends, but the ends are always going to do the same as long as your leading coefficient test, so your leading term, the power is odd and the coefficient is positive. You're going to have, as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x approaches negative infinity. Now, if we have an odd power, but the coefficient is negative, so we have a negative x to the n, where n is odd, it's going to flip it around so that as x approaches infinity, f of x goes to negative infinity, and the opposite for the other side. And again, it could do all sorts of things in between the ends, but the ends, as x approaches infinity, f of x is going to approach negative infinity, and as x approaches negative infinity, f of x approaches infinity. So if you're looking at the graph, as I go out, as x is going to infinity, my y is going to negative infinity. If my x is going to negative infinity, my graph is going to infinity. So that's how you write that, or the notation you use. Now the other situation, if your power is even, but your coefficient is positive, it's going to do what the x squared, a quadratic, would do. Both ends will go up. Now it could do, again, all kinds of twists and turns, but the ends will both go to positive infinity. So as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x approaches infinity. And then the opposite, if your leading coefficient is negative, it's going to flip it down. So let's say we do something like that. It's going to say as x goes to infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x goes to negative infinity. So just depending on if the power is even or odd, and if the leading coefficient is positive or negative, that tells you a lot about the end behavior of the graph. So, for example, if we want to describe the end behavior of the function, we find our leading term. This one has an odd exponent, and it's negative. So what that tells us is it's going to look like this. Oh, sorry, this one, because it's negative. So that means as x approaches infinity, it goes to negative infinity, and as x approaches negative infinity, f of x approaches infinity. So just get used to this notation. It looks a little scary at first, but it's just, if you read it in words, it makes a lot more sense than just looking at it. Okay, the next one, I'm looking at the 2x to the fourth. So I have an even power, and I have a positive coefficient. So that means it's going to look like a quadratic. So as x approaches infinity, f of x approaches infinity, And as x approaches negative infinity, f of x approaches infinity. And then the last one, we've got our leading term is a negative 1/2 x to the 6th. So our power is an even number, and we've got a negative coefficient. So that means it's going to flip both ends down. So it's just going to be switched from the previous one. Both are going to go to negative infinity. So now it's time to kind of put it all together. We've got a graph here. Given the graph, we want to determine the least possible degree and whether it's even or odd. And just look at the intercepts and the turning points. So if you look at here, at this graph, we've got 2x intercepts, but we have 3 turning points. So what that tells me is that your degree or your turning points n minus 1, if that equals 3, then n has to at least be 4. So the degree has to be at least 4. Even though we only have 2 intercepts, that's the at most it can have, is the how it works. So if n is 4, it doesn't have to have 4 intercepts. It can have less than that. So don't just look at the intercepts, look at the turning points too. We also know that both ends are going to infinity, so that tells me that my degree is going to be an even degree because they're both going the same direction. And since they're both going up, I know the leading coefficient is going to be positive. So if I was going to write a formula for this, I would know the first term had to be a positive x to the 4th, just from looking at the graph. Now, what else you can do with that is you can actually sketch the graph from all putting everything together. If I look at this one, I've got 2x cubed. That tells me that my power is odd and my coefficient is positive. So that tells me it's going to look like the x cubed graph, where as x goes to infinity, f of x is going to go to infinity. And as x goes to negative infinity, f of x is going to go to negative infinity. I also know that I could have 3 x-intercepts, and I can have at most 2 turning points. Now, with all that information, we can find our x-intercepts and our y-intercepts. Let's start with the y-intercept because it's pretty easy. The y-intercept, you just plug in 0 for x. So if I plug in 0 everywhere there's an x, I come out with 0. So what that tells me is my graph is going to intersect the x-axis at 0. So I've got 0, 0, or the origin. Now the harder one here is the x-intercepts, where you set y equal to 0. So here I'm going to set the whole equation equal to 0 and solve for x. Well, if you notice, every term has an x. When that happens, go ahead and factor out the least common multiple or the least common denominator, whatever they have in common. So here I can pull out an x out of every term, and I can actually go ahead and pull out a 2x because each coefficient is divisible by 2. So that's going to leave me with x squared minus 3x minus 10. And then that will factor pretty easily. I need factors of 10 that add or subtract to be -3. It's going to be subtract here because I have a minus and a minus. So that's going to be -5 plus 2 to get me the -3x. Now I'm going to set each term equal to 0. So I've got x equals 0, which is also my y-intercept. I've got x equals +5 and x equals -2. So I'm going to have that 0, 0. I'm going to have an intercept at 5, 5. And I'm going to have one at 2 or -2. And then I also know that this end is going up and this end is going down. So I don't know exactly what this graph looks like, but I know that it's got to at some point turn back around and go through these intercepts. So if I was to graph that, it would be similar to that. And notice I have 2 turning points and 3 x-intercepts. You could do the same one with the same thing for this. X to the 4th, it's positive and even, so I know both ends are going to go up. If I factor this, well, let's do our y-intercept first. If I plug in 0 for every x, I got 0 to the 4th minus 4 times 0 squared minus 45. So that's going to be f of 0 equals -45. So that is one of my intercepts, 0, -45. So if I made these by 5s, 5, 10, 15, 20, 25, 30, 35. Well, I still run out. Let's do it by 10s. So if this was -10, 20, 30, 40, 45. So that would be -40. Halfway between it would be -45. That's one intercept. This one, it's not a quadratic, but we can treat it like a quadratic. We did this earlier in one of the chapters, where if you let u equal x squared, then u times u would equal x to the 4th. So we can factor this as u. Well, let me rewrite it in terms of u first. I can rewrite that whole thing as u squared minus 4u minus 45 equals 0. Factor that, I'm going to have a -9 and a +5. Now I'm going to resubstitute x squared back in for u and set each one equal to 0. So I've got x squared equals 9, square root both sides, x equals ±3. Here I've got x squared equals -5. So when I square root both sides, I get x equals ± square root of 5. That's not a real number, so that's not going to show up on my graph. So I'm just going to have x-intercepts at 1, 2, 3 and -1, 2, 3. Okay, so I don't know exactly what this graph is doing either in between, but I know the ends are going up, and I know that it could be curving more in there, but that gives me a general idea of what's happening, where it's crossing the axis, and what the ends are doing. We'll go in later where we actually plot some points and do some actual sketching of the graph.